Now we want to start talking about some masses and how those relate into what we've done so far. So we know our goal was to perform chemical reactions. We need a certain number of atoms. We want to efficiently count them. And so moles help us do that, count by groups. But the question is, how do we figure out the mass of that? We don't have any equipment that can just measure a mole of lead atoms. So how can we figure out the mass of a mole of an amount or some sort of thing like that? And so the question we want to ask is, what's the mass of a molecule? And so when we get into these ideas of starting to talk about mass and moles, it's kind of worthwhile to take a second to think about what these things even mean. Okay, so mass is asking the question of how much. This is generically just an amount of matter in a sample. So matter being like protons, neutrons, electrons in there. And in general, we really don't care when you're measuring mass what that mass is. 10 grams is 10 grams. It is just a measurement of how many, like literally subatomic particles are jammed into that. It doesn't matter what sort of atoms they're distributed in, or even how many atoms are in there. Are they big atoms, small atoms, anything like that. So mass tells you how much stuff is in there independent of where that stuff is located, what the volume of it is, or anything like that. And so that's a how much question. So it's an uncountable amount. Moles is a count of how many. You are now asking about a number of objects. So in this case, you care where the matter is. Are you dealing with atoms? Are you dealing with molecules? Are you dealing with formula units, ions? What is it that you are looking at? And so moles is going to give you the number of objects. And so the question, if you have a sample of matter for how many objects are in there, how many atoms, depends on the size of the atoms, depends on the types of the atoms, things like that. Really small atoms, you need a lot to get to a certain size mass. Really, really big atoms, big molecules, you don't need as many of those molecules to get to a certain mass. The important thing is that mass and mole measurements can describe the exact same sample, right? So a certain number of molecules has a certain mass. And so the question then is just, how do you choose to describe something? And because we just use mass more frequently, just because you can generically describe anything, right? Just the amount of matter in the sample. So 10 grams is 10 grams. You only need one piece of equipment, a balance or scale, to measure the mass of anything. For moles, you could theoretically make a mole measuring piece of equipment, but you would have to be measuring one particular pure substance in order for that number to mean anything. And that's a much harder thing to produce, so we just use mass measurements instead. So the original question, what is the mass of a molecule? The definition of that is called the formula mass. So formula, if we think of it, it's the molecular formula that we're talking about here. So it's just the mass of a formula. So that could be a molecule, a formula unit, whatever you're looking at. In order to compute the formula mass, you use the average atomic masses from the periodic table. Those are the mass values that are on the periodic table. So for example, H2O, in our formula, we can see that we have the 2 hydrogen atoms and then just 1 oxygen because there's no number written there. So if we want to figure out the mass of the molecule, we need to figure out the mass of the 2 hydrogen atoms, and then we have the mass of the 1 oxygen atom. And so then we can go and look at the periodic table and pull off these masses right here. You'll note when you look on the periodic table, you only see the numbers. So for example, hydrogen 1.01. The units on there are AMU, atomic mass units. The units are not written, and we'll see why in just a little bit. And for oxygen, you could find 16.00. Your periodic table, if you use the one that's in the additional resources or any of the other ones that have been here or in the book, you'll note there's a lot more digits after the decimal that they are displayed. I just use 2 digits after the decimal. So I always round my atomic masses to 2 digits after the decimal. The reason for that is because that's generally enough for sig figs. And you'll note not every atom type has a lot of digits after the decimal. And so you can just be consistent. I always use at least 2, and it just makes sig figs a bit easier because you're multiplying these things out. You have some exact numbers in here, then you're adding. And so you care about digits after the decimal for rounding. And this way your answer always has 2 digits after the decimal. So I just always use 2 digits. when I pull them off the table, I just round to that, and then I can round my answer to 2 digits as well. You can use more if you like. You can't use less. You do want to use 2. You don't want to have the molar mass be a limiting factor. If you think about it, we're generally going to use these formula masses in multiplication problems. And right now here I'm looking at 4 sig figs. So I'm unlikely to round a multiplication problem based on these 4 sig figs. And so that's generally going to be enough. But I don't want to limit it. I don't want to say cut off all the decimals and then say only have 1 sig fig in this formula mass. We really don't want to look at that. We want to have a total, a lot of sig figs in there. Enough. 4 is generally enough. 8 is a bit overkill. So let's actually work through an example. What is the formula mass of chloroform, which is CHCl3? When we're going through and calculating, when we're looking at this, starting what do we want? When we see formula mass, this isn't really necessarily a problem-solving issue. There's no conversion factors. This is a process. And the thing that we need to facilitate that process is the molecular formula. Okay, we want to take this molecular formula, and then we can use our atomic masses, which are on the periodic table. Okay, so it's going to be a matter of taking the formula that we're given, the molecular formula, figuring out the number of atoms, and then turning that into number of atoms, and then plugging that into with the atomic masses from our periodic table. What is the formula mass of chloroform, which is CHCl3? So computing the formula mass of a compound is just a matter of taking that formula and using the periodic table. When we look at CHCl3, we want to parse out what types of atoms we have and how many do we have. So you can see 4 types of atoms. I have C, H, and Cl. And then I have 1 of the C's, 1 of the H's, and 1 of the Cl's. So doing this calculation is going to be 1 times whatever carbon is, plus 1 times whatever hydrogen is, plus 3 times whatever chlorine is. And so because the mass for chlorine that I'm going to pull off the periodic table is, I know, for 1 atom, and here I have 3 of them. So I want to make sure that I use all 3 of those. So I can come to the periodic table, I can look carbon, see it's 12.011. I'd prefer, I'm just going to round that to 2 digits after the decimal point. So that way I get 1 times 12.01. And the units aren't given on the periodic table, but whenever I'm putting formula mass, those units are AMU, the atomic mass units. I have 1 hydrogen. I come back, I find hydrogen on the periodic table, 1.008. I'm going to round that to 1.01 AMU. Plus 3 times chlorine is, I find chlorine, Cl right here, 35.45. One of the things we can see, chlorine doesn't have any more digits after that. This is why I use the 2-digit rule after the, whenever I'm pulling these values off the periodic table. So that way, because we're going to multiply these together and then add them, for sig figs, we care about digits after the decimal point. Chlorine has 2 digits at that point. That's that's generally most everything. That's the lowest they have. So if I just always use 2 digits after the decimal point, when I go to compute my formula unit at the end, I'm always just going to have 2 digits after the decimal point for sig figs. So I don't have to worry about how I round in this particular problem. If you go crazy with like these 3, 4, 5 digits after the point on like some things, it requires thinking about rounding, and I'd rather not have to think about it. Just automatic. Always leave 2 digits after the decimal point. So I've gotten all of my values. The 12.01 AMU for carbon, 1.01 for the hydrogen, and the 35.45 for chlorines with the 3 of those. So if I take those, combine them all together, I get 119.38 AMU. And so I can always calculate the formula mass for anything that I'm looking at based on if I know the formula and if I have access to a periodic table. So now that we know how to measure the mass of, determine the mass of one molecule, we want to go back to thinking about groups, right? And so when we talked about counting units, we had just say a certain number of objects. So now we want to think about what the mass of that number of objects would be. So if we think about, say, a dozen, that's 12, we know. We know that a dozen mice weighs, say, a small amount, because each mouse is small, whereas a dozen elephants weighs a lot because each elephant is really big. They are both still a dozen, right? So when we're in these counting descriptions, the size, the number of objects in that group is the same, but the properties of those groups may be distinct. You have a much larger mass for a group that has more things in it, okay? Or has larger objects in it, because they have 12 objects in each. Whatever has the bigger objects is going to have a larger mass. If we start thinking about the chemical context, different atoms have much different sizes. Lithium, for example, the nucleus is 3 protons, 4 neutrons. If you have, say, one lithium nucleus, or one lithium atom, not a very large mass. Lead is really big, 82 protons, 126 neutrons. There's a lot in there. So each lead atom has a much higher mass than each lithium atom. So if you got a group of them, if you got groups that were the same size, mole of lithium, mole of lead, those masses are going to be different. Because each lithium atom is smaller, a mole of lithium is going to have a smaller mass than a mole of lead atoms. Same number of objects, different size objects. So the mass of a mole depends on the substance that you are counting. Different atoms have different sizes, small atomic numbers, really small, like say hydrogen. Big atomic numbers like lead have much larger masses. And then if you think about molecules, you could say have small atoms in molecules or just large numbers of atoms. Sucrose, for example, there's not really much big in a sucrose. Carbon, hydrogen, oxygen, none of them are large atoms. There's just a lot of atoms in that molecule where the formula mass starts to creep up. You're looking at 342 AMUs. That's much bigger than, say, a single large lead atom. So if you have these bigger and bigger molecules or bigger and bigger atoms, the mass of the individual object is bigger or smaller, depending on what you're counting. And so the mass of a mole is going to depend on the substance. So we quantify this mass of a mole by what's called the molar mass, which the definition of that, it is the mass of 1 mole of a substance. The units that we see on that are going to be grams per mole. With the formula mass, we just reported them as AMU because we were looking at the mass of 1 molecule. That was kind of defined. Even though it's the mass of 1 mole, we do explicitly include that MOL in our unit for molar mass, grams per mole. Okay, so one of the things we can see, this is a compound unit that we can see right away. The molar mass, the value of the molar mass is unique for a substance. Whatever you're counting, atoms, molecules, formula unit, whatever is in your package, your group, that's the size of a mole. When we go about the process of calculating molar mass, it is numerically equivalent to the formula mass in atomic mass units. The only difference is that the units are in grams per mole. So the process we just used for calculating the formula mass is going to be the same way that we calculate the molar mass. Okay? So the reason why this is true is this is where Avogadro's number comes from. This kind of seemingly random. Why didn't we just use 10 to the 23rd or 10 to the 24th? 6.022 times 10 to the 23rd, a single molecule of water has a mass of 18 atomic mass units. A mole of water has a mass of 18 grams. The only difference is that mass. So basically, we just picked the atomic mass units, about 1 proton, right? And we just picked the number of objects in a mole such that this equivalence would be the case. So we're going to go through the process. What is the molar mass of chloroform? So I got CHCl3, molar mass of chloroform. I'm going to start, what is the molar mass? And so we know, just like for calculating formula mass, this is going to be the same, it's going to be an algorithmic process. What we need for it is the molecular formula. Okay, so we can take that molecular formula. Again, we can look up the masses for the individual atoms on the periodic table and use those. So we're going to look for these atomic molar masses on the periodic table. The molar mass and formula mass are numerically equivalent though. So this is the same exact process that we saw for doing the formula mass. We're going to use the exact same process. We'd expect to get the same number. So when we actually go about doing it, we can see that we get these exact same numbers. We get the 12.01 for our carbon. We still have one carbon because it's the exact same formula. This is still chloroform, so we get the same idea. The only difference is that our units are different. We now call this gram per mole. That is why there are not units listed on those mass numbers on the periodic table, because they can represent both atomic mass units and grams per mole. But numerically, they are identical. So the mass of one molecule of chloroform is 119.38 AMUs. The mass of one mole of chloroform is 119.38 grams. So computing the molar mass is something we can always do as long as we know what the molecular formula is and we know what we have access to a periodic table. So periodic table, we're going to see it's going to come back again and again. It's the first time we're really going to be using it to calculate these molar masses.